Hello my dear students, in this lecture series of IIT JAM, GATE, NET and SET etc. exams, in this video we are going to discuss about the basic principles of NMR spectroscopy. NMR stands for Nuclear Magnetic Resonance. We know that due to the spinning property, a nucleus possesses a spin magnetic moment and it behaves like a magnet. In presence of an external magnetic field, if this magnet aligns itself in the direction parallel to that of the external magnetic field, then the spin of the nucleus is called alpha spin. And on the other hand, if the nucleus aligns itself in the direction opposite to that of the external magnetic field, then the spin of the nucleus is called beta spin. Now, when such a nucleus is placed in an external magnetic field, a magnetic resonance arises due to the interaction of the external magnetic field with the magnetic moment of the intrinsic spin of the nucleus. And when the different orientations of the nuclear spin magnetic moment interact with the applied magnetic field, that leads to nuclear magnetic resonance. Now, if the nucleus is subjected to the exposure of a radio frequency radiation, then by absorbing energy from the radio frequency radiation, the nucleus undergo excitation to the higher energy levels and align itself in the direction opposite to that of the external magnetic field. The radio frequency radiation absorbed by the nucleus is then plotted against the magnetic field strength to record the NMR spectrum. From the NMR spectra thus generated, we get various informations about the molecule. The difference in energy between the two spin states is given by delta E is equal to Gn beta n B0, where Gn is called the G factor and its value is 5.585 for the proton. Beta n is called the nuclear magneton and its value is given by 5.05 into 10 to the power minus 27 joule per Tesla, while B0 is the strength of the external magnetic field. Now let us discuss about the construction of a typical NMR spectrometer. A typical NMR spectrometer consists of the following 5 components: a radiofrequency source of radiation, a holder containing the sample, a strong electromagnet, a radiofrequency detector, and a recorder which is attached to a printer. Let us discuss about how a NMR spectra of a sample is taken. So first of all, a sample is placed between the poles of the electromagnet whose field strength is varied by means of current produced in a sweep generator. As each nucleus of the sample is brought to the resonance, it absorbs energy from the oscillator, and when it reverts to the ground state, the emitted energy is collected by the detector and then it is amplified and is passed to the recorder. The radio frequency radiation absorbed by the sample is then plotted against the magnetic field strength recorded by the recorder, and thus the NMR spectrum is generated and we can export it or take out the print copy. There are two types of NMR spectrometer: continuous wave or CW NMR spectrometer and Fourier transform NMR spectrometer or FT NMR spectrometer. In the CW NMR spectrometer, the applied magnetic field strength or field sweep is kept fixed and the radio frequency is swept through a given range. Therefore, it needs 5 to 10 minutes for completion of the process and it is known as frequency sweep. On the other hand, in the FT NMR spectrometer, the radio frequency is applied not as a continuous beam of monochromatic radiation but as a short pulse covering the whole range of frequencies lasting only for a few microseconds. The Fourier transformer or FT is the operation. Actually, it is a mathematical operation which involves the individual frequencies from the interferogram to form a spectrum. As a result, it needs very short time to record the NMR spectra. In a nuclear magnetic resonance process, a single radio frequency, which is shown as rectangles, such a pulse is applied to a system followed by observation of the free induction decay or FID as a function of time. Now, Fourier transformation of this function gives the NMR spectrum as a function of frequency. This type of NMR spectrum is called one-dimensional NMR spectrum. In addition to the normal single resonance experiments, many other NMR techniques have been developed. By applying a second radio frequency at right angles to the magnetic field, the observed spectrum may be perturbed, from which more information about the system may be gathered indirectly. Such NMR technique is called double resonance NMR. Internuclear double resonance (INDOR) is especially useful when a multinuclear NMR instrument is unavailable because it gives details about one type of nucleus only while irradiating only a different type. In INDOR, the sample is simultaneously exposed to the radio frequency of two different frequencies, one frequency being used to observe radiation absorbed and the second frequency is used to produce a perturbation that affects the spectrum. Now let us talk about the relaxation process. The excited nuclei release excess energy and come back to the ground state with or without emitting the radiation. This process is known as relaxation process, and there are two types of such relaxation processes. The first one is spin lattice relaxation and the second one is spin-spin relaxation process. In the spin lattice relaxation process, the excited nuclei transfer their excess energy to the surrounding framework of molecules or lattice and come back to the ground state or lower energy spin state. On the other hand, in the spin-spin relaxation process, the excited nuclei transfer its excess energy to another molecule in the ground state and releases down. The latter, in turn, gets excited by absorbing energy. In this relaxation process, energy transfer takes place between two nuclei of the same type having the same processional frequency. Now let us solve some numerical problems based on NMR. In the first example, we have to calculate the magnetic field strength required to get a transition frequency of 60 MHz for fluorine. The value of Gn is given as 5.257. This is a very simple problem. We can use the relationship delta E is equal to Gn beta n B0, and we know that delta E is equal to H nu 0. From this expression we can write B0 equal to H nu 0 by Gn into beta n. Now substituting the values of H nu 0, Gn and beta n, we get the value of B0 as 1.4973 Tesla. But remember that the value of nu 0 is given as 60 MHz. You have to convert this value into Hertz. Therefore, the value of nu 0 is taken as 60 into 10 to the power 6 second inverse or Hertz. In the second problem, we have to calculate the precessional frequency of a proton in the field of 1.8 Tesla. This problem can also be solved by using the relationship delta E is equal to Gn beta n B0, and since we know delta E is equal to H nu 0, therefore we can write H nu 0 is equal to Gn beta n B0, from which we can write nu 0 is equal to Gn beta n B0 by H. Now substituting the value of Gn equal to 5.05 into 10 to the power minus 27, the value of beta n as 5.85 and the value of B0 is given, which is 1.8, and the value of H, it is known to us as 6.627 into 10 to the power minus 34. Now simplifying this, we get the value of nu 0 equal to 7.66 into 10 to the power 7 second inverse or hertz. Dear students, I am giving you 2 more problems for your homework. Solve these 2 problems and let me know the answers of these 2 problems in the comment box. Although the theory of NMR spectroscopy is not that much easy to understand, but still I have tried my best to explain the theory of NMR in a brief way. In my next lecture, I will try to discuss the various other aspects related to the NMR spectra and also discuss about the pattern of NMR spectra of various molecules. Please do subscribe my channel so that you get the notification for the next lecture as soon as it is uploaded. Thanks to all of you for your patience.